steady flow to well in confined aquifer. So this below is a confined aquifer because there is a in previous layer on the top and the bottom the water flow in the confined aquifer, and once we make a wells to the confined aquifer, the water will be moving up to this level. This. So this we call the original piezometric surface. Okay. Next we make a hole. Okay. And just we start to pump the water from the aquifer. The piezometric surface is going down like this. When time is increased, the piezometric surface is moving down like this. So until it comes to this point, it means it's steady state. It means it doesn't change anymore. It's steady. Okay. And at one point, that we call the inference radius. Inference radius is mean the point that the water level piezometric surface is the same level, maybe somewhere in this. Okay, so it means the water level is the same. For the velocity, is this point. Okay, so this point is mean at the radius r. We can estimate the flow. The first thing we can estimate velocity passing through this aquifer, because the area is b. So it's in this case, its area of the flow is equal to 2 pi and times the b, so for the area of the flow. So we can estimate use the Darcy velocity to find start from Darcy velocity and time the q, time Darcy velocity with the area. Okay, because of q is constant pumping rate, so we can do rearrange equation and integration to get the equation of q. So we integrate equation from rw to rv to ri sw to hi. So it means we integrated from rw to ri, or sw is mean the hydraulic head at the pumping well to hi or hi. So finally we got this equation for steady flow from confined aquifer. And this figure should show the profile of the piezometric head. When water level, when the decrease of water level in the well, we call the drawdown. Okay, the curve that present the piezometric surface, we call the drawdown curve, or we look at in terms of 3 dimensions, is we call the cone of depression. Okay. So this. And to start from flow equation, we already derived this flow equation from previous lecture. And if we assume that flow is on x and y direction, is no flow on the z direction, so we can cancel the flow on z direction. So only have the flow on xy direction. And for flow to the well, the movement of the water is in the radius and theta. So we can convert to make it convenient to the Lect equation. We convert from reference point and rectangular coordinate to polar coordinate. Okay, from xy to theta. That will, because of the water flow to the center of the well. So it fit to this the coordinate, and we can convert the both equation to this equation respect to r and theta. Okay, and if the flow is a steady flow, okay, and the unsteady term del h over del y is 0, so we can cancel this term. And if next we assume that the flow is ideal symmetry, h is function of radius, so this term is go to 0, so we can cancel this term. So we can come up with just only one term of the partial differential equation. And the next we can do the integration once and twice. Once we have constant d1, twice we have d2. The next we apply the two boundary condition HW, RW, HI, RI, and to get the constant d1, and to get the constant d2, and so we can derive equation of the h. H is a function of the radius. Okay. So in this means we can this curve represent draw down curve in the confined giver. Okay, at any radius, and we can find the hydric head h. So this curve can represent this equation can represent this curve. Okay, we can estimate hydric head at any radius. Okay, for the equation of flow Q, we can based on this equation, we substitute that del h over del r from the above, and we can estimate the similar steady flow equation for Q. Okay, just substitute this term, substitute d1 and move to this. Okay, so we can estimate Q.